At first, there was a boundlessly thick mass of issue. This mass went through a shift that prompted the development of particles, molecules, stars, and universes that we can see today. For many years, this has been the explanation presented by physicists. However, later research has introduced a new perspective suggesting that the universe doesn't have as early a beginning as initially believed. Rather, it may be part of a repetitive cycle in which the universe goes through a series of patterns of expansion and contraction, possibly in a boundless circle. Brian Cox, a renowned physicist, has expressed skepticism about the theory of the ancient Big Bang, arguing that something cannot arise out of nothing. This questioning adds a fascinating dimension to the discussion. Furthermore, research from the James Webb Telescope has revealed data conflicting with the idea that the Big Bang marked the definitive beginning of the universe. This raises the crucial question: if the Big Bang was not the beginning of the universe, then what was? Join us on this journey to the origins of the universe, where we will explore the unresolved aspects of the Big Bang and answer this question, and more. If you are excited about staying updated with news about the universe and its surroundings, subscribe to our channel. Hit the like button, share this video to reach more people, and turn on notifications. Scientists have developed a detailed understanding of the universe in its earliest stages, known as the theory of cosmic origins. According to this model, the universe was much smaller, hotter, and denser than it is today, around 13.8 billion years ago. During that period, all the components that make up our existence were formed almost instantaneously. In this theory, our universe, including stars and galaxies, was once as small as a peach and had an extremely high temperature of over a quadrillion degrees. Interestingly, this extraordinary account aligns consistently with all current observations. Astronomers have studied everything from the remnants of electromagnetic radiation from the early universe to the distribution of the lightest elements, and have found that everything matches the predictions of the Big Bang theory to the best of our knowledge. This description fits the reality of our universe perfectly. However, despite its apparent accuracy, we know that the theory of cosmic origins is not the complete picture. There is a missing piece of this puzzle, a deeper understanding of the universe's initial moments. This challenge largely stems from the limitations of the physical theories we currently use. The combination of general relativity and high-energy particle physics provides a crucial framework. However, as we delve further into the universe's earliest moments, the mathematical complexity increases dramatically, reaching a point where our current methods cannot provide meaningful solutions. One indication of this difficulty is the concept of a singularity, a point of infinite density near the beginning of the Big Bang. This idea suggests, quite literally, that the universe was once compressed into an infinitely small and dense state, which seems implausible. To address this challenge, we need to explore new frontiers in physics and develop methods that overcome these limitations, providing a more complete understanding of the universe's earliest moments. Our current tools and theoretical frameworks are not robust enough to meet this challenge. Thus, we must develop new physics capable of unifying gravity and the other fundamental forces at extremely high energies. This is precisely where string theory comes into play. This theory aims to be a physical model capable of unifying gravity with the other fundamental forces, especially at ultra-high energies. Essentially, string theory claims to provide an explanation for the universe's earliest moments. Within string theory, the concept of an ion emerges, named after the Greek word meaning cycle or age. This idea suggests that the Big Bang was the result of a prior event, implying that it was not the absolute beginning but part of a continuous cycle. Expanding on the idea of a cyclic universe has led to the development of a related theory called cyclic cosmology. Although the possibility of a cyclic universe has been considered for centuries, string theory provides a strong foundation for this concept. In the framework of cyclic cosmology, the universe functions like a pendulum, endlessly oscillating between big bangs and contractions in a perpetual cycle that stretches infinitely into the past and future. This hypothesis of cyclic cosmology was proposed by the renowned physicist Roger Penrose, who was awarded the Nobel Prize. Penrose was intrigued by a significant mathematical relationship between the early universe, characterized by extreme density, heat, and smallness during the Big Bang, and the universe's future state, which is extraordinarily cold, vast, and devoid of matter. The theory suggests that these two states become mathematically indistinguishable when pushed to their limits. Paradoxically, the total absence of matter could be the driving force behind the creation of all the matter we observe in the universe. From this perspective, the Big Bang arises from what remains, almost enigmatically, after all the matter in the universe has been consumed by black holes, which eventually evaporate into scattered photons in a massive void. The universe emerges from what, in another view, approaches nothingness. Although this nothingness is still a form of something, a true universe though an empty one, the paradox lies in how the same state can be interpreted as both a cold, empty universe and a dense, hot universe depending on the perspective. The key to this understanding lies in a complex mathematical technique called the conformal transformation, a transformation that changes an object's size while preserving its shape. Roger Penrose demonstrated that the cold, empty state and the hot, dense state can be connected through this scale transformation, altering their spacetime structures despite their vast differences in size. However, Penrose argues that the concept of time loses its significance under these extreme conditions. In cyclic cosmology, the sequence of events evolves from an old, cold state to a young, hot state. The presence of the hot, dense state results from the prior cold, empty state. However, this causal relationship does not follow the conventional notion of time. As in these extreme states, both size and time lose their traditional meanings. The cold, empty state and the hot, dense state exist on discrete timelines, meaning that, from the perspective of an observer within its own timeline, the cold, empty state would persist indefinitely. Physics and philosophy intertwine in this realm of cyclic cosmology, providing speculative and detailed explanations for the origins of these cycles. Regardless of whether Penrose's ideas gain widespread support in cosmological advancements, a deeper philosophical question still lingers about the ultimate origin of physical reality. The idea of cyclic cosmology challenges the traditional notion of a single, definitive beginning for the universe. If time itself loses meaning at these extremes, it opens the door to a fundamentally different understanding of existence. Rather than imagining the universe as having a starting point, we might instead view it as part of an infinite loop or cycle, with no true beginning or end. Such a perspective raises profound questions. What governs the transitions between these cycles? Are they purely physical, driven by the fundamental laws of nature, or is there an underlying principle yet to be discovered? And if the universe oscillates between cycles, does each new cycle retain any trace of the previous one, or is every cycle entirely new, leaving no memory of its predecessors? One key area of exploration in this context is entropy. In classical thermodynamics, entropy, a measure of disorder, always increases in a closed system. This principle raises a challenge for cyclic cosmology. If entropy increases with each cycle, would it not eventually render the universe incapable of starting anew? String theory and Penrose's work suggest potential resolutions to this problem, but it remains an active area of research. Furthermore, this exploration touches on deeper philosophical and metaphysical questions. If the universe is cyclic, what does that imply about its purpose or meaning? Is the cycle itself the essence of existence, or could it hint at something beyond, a greater structure or reality that encompasses the cycles? Interestingly, advances in observational astronomy, such as data from the James Webb Space Telescope, continue to challenge established cosmological theories. For example, the discovery of ancient galaxies that appear to defy current models of early universe formation suggests that we may be missing key pieces of the puzzle. These observations could provide critical insights into whether the universe's history aligns more closely with a singular Big Bang or a cyclic model. Looking ahead, the unification of quantum mechanics and general relativity, the two pillars of modern physics, is likely to play a crucial role in resolving these mysteries. Theoretical frameworks like string theory, loop quantum gravity, and conformal cyclic cosmology offer promising avenues for exploration, but experimental validation remains a significant challenge. As our understanding deepens, we may find that the universe's true nature is far more intricate and interconnected than we ever imagined. Whether through the lens of a cyclic cosmology, a multiverse, or an entirely new paradigm, these investigations push the boundaries of human knowledge and invite us to reconsider our place in the cosmos. How did these cycles appear? This leads us to ponder the support for the presence of something different from nothing, which is one of the essential otherworldly questions. For the purposes of our discussion, we will focus on explanations within the realm of physics, considering three possible outcomes for the origins of these cycles. First, there may be no obvious explanation at all. Second, there could be an endless series of cycles, where each cycle represents a different universe, and the initial quantum state of each universe is somehow determined by a component of the previous universe. Finally, there is the possibility of a single cycle in a repeating universe, where the origin of the cycle is explained by some aspect of its own end. These possibilities are intriguing because they avoid the need for uncaused events and provide a more complex explanation within the physical framework. Roger Penrose's continuous cycles. Physicist Roger Penrose proposes the idea of a continuous sequence of cycles, influenced by his interpretation of quantum mechanics. In quantum mechanics, a physical system exists in multiple states simultaneously until it is observed, at which point it randomly collapses into a single state. Penrose suggests that each cycle is affected by random quantum events, leading to variations between cycles. This idea opens up exciting opportunities for experimental physicists, as it suggests the possibility of identifying subtle traces or anomalies in the residual radiation from the Big Bang. The quest for cosmic origins. The mission to understand the origins and nature of the universe has been a central pursuit of human curiosity and scientific inquiry for centuries. From ancient philosophical theories to modern cosmological hypotheses, humanity has persistently sought to unravel the mysteries of existence itself. In the context of contemporary astronomy and cosmology, the exploration of cosmic origins has led to significant discoveries and compelling theoretical frameworks that challenge our fundamental understanding of time, space, and matter. One of the enduring questions that has fascinated physicists and cosmologists alike is the nature of the universe before the Big Bang. While the Big Bang theory provides a convincing explanation for the evolution of the universe from a hot, dense state to its current vast structure, it leaves open the question of what preceded this cosmic event, if anything. Pre-Big Bang theories. Multiverse and eternal inflation. The concept of a pre-Big Bang era raises profound philosophical and scientific implications, pushing the boundaries of our knowledge and understanding. Several theoretical frameworks have been proposed to address this question, each offering novel insights into the early universe. 1. The multiverse hypothesis. One such idea is the multiverse theory, which posits the existence of a vast collection of universes, each with its own distinct physical properties and fundamental constants. In this framework, our universe is just one among many, each arising from different initial conditions and governed by its own set of physical laws. The possibility of a multiverse arises naturally from certain interpretations of quantum mechanics and cosmological inflation theory. According to inflationary cosmology, the rapid, dramatic expansion of spacetime in the early universe could have led to the creation of pocket universes within a larger multiversal landscape. Each pocket universe would have unique properties, shaped by random quantum fluctuations during the inflationary epoch. 2. Eternal inflation. Another intriguing concept is eternal inflation, proposed within the framework of inflationary cosmology. Eternal inflation suggests that the universe undergoes an endless cycle of inflationary phases, each leading to new regions of spacetime with potentially different physical laws. In this scenario, our observable universe is just one of countless regions within an eternally expanding cosmic foam. This idea raises profound questions about the nature of time and causality in the multiverse. If inflationary bubbles generate new universes indefinitely, the notion of a single beginning or ultimate origin becomes increasingly elusive. Cyclic universe models. In recent years, advances in theoretical physics have also sparked interest in alternative cosmological models that challenge the traditional narrative of cosmic origins. For instance, some theorists have explored the possibility of a cyclic universe, where the Big Bang is not a single event but rather one phase in an eternal cycle of cosmic expansion and contraction. According to cyclic cosmology, the universe undergoes successive cycles of creation, expansion, and destruction, each ending in a cosmic collapse followed by another Big Bang. The cyclic universe theory draws inspiration from ancient cosmological ideas and modern theoretical frameworks, such as string theory. In string theory, which posits that fundamental particles are not point-like objects but rather tiny vibrating strings of energy, the concept of a cyclic universe naturally emerges from certain solutions of the theory. Observational insights and future prospects. Observational cosmology has provided crucial insights into the early universe and its evolution over cosmic time. The discovery of the cosmic microwave background (CMB) radiation in the 20th century offered undeniable evidence for the Big Bang theory, providing a snapshot of the universe when it was only 380,000 years old. Detailed measurements of the CMB by satellites, such as the Planck Observatory, have enabled scientists to map variations in temperature and density across the early universe with remarkable precision. Observational cosmology has also shed light on the large-scale structure of the universe, revealing the intricate web of galaxies, clusters, and massive filaments spanning billions of light-years. One of the most remarkable discoveries in observational cosmology is the presence of dark energy, a mysterious form of energy driving the universe's accelerated expansion. First detected through supernova observations in the late 1990s, dark energy accounts for approximately 68% of the universe's total energy density. Its origin and nature remain poorly understood, posing a significant challenge to our current understanding of fundamental physics. The future of cosmic exploration. Looking ahead, the next generation of observatories such as the James Webb Space Telescope (JWST) and the Square Kilometre Array (SKA) promises to unlock new insights into the early universe and its fundamental constituents. These cutting-edge instruments will enable scientists to study the first galaxies, probe the reionization epoch, and search for traces of primordial gravitational waves left over from the Big Bang. In conclusion, the quest to understand the origins of the universe represents one of the greatest intellectual challenges of our time. From ancient myths and philosophical inquiry to modern scientific theories and observational discoveries, humanity's exploration of cosmic origins has yielded profound insights into the nature of reality. As we continue to push the boundaries of knowledge and exploration, new theoretical frameworks, observational techniques, and experimental breakthroughs will undoubtedly shed light on the deepest mysteries of existence and our place in the universe.